Hello. In this talk, I want to go over how different types of programming languages interact with your computer when they run their code. So, you may have heard different terms like compiled language or interpreted language. You might have heard something like just-in-time compiled. You may hear about runtimes and virtual machines. So the question is, what does all this stuff mean? So I've covered in a previous talk, I think it was number 2, about state in computing and how computers of the current day are essentially just state management machines. They hold data in different places, synchronize that data, help you to do math on that data and move it around. And everything that they do is pretty much built on that small set of capabilities. So what's happening when you run the most basic types of programs, or the most kind of efficient, close to the machine types of programs, is you have binary code, zeros and ones, machine code, that just runs through your processor like it's an assembly line. It's just going in. You can think about it like going in one side, getting processed, and then coming out the other side, or the effects of that, coming out the other side, so to speak. Nothing actually comes out the other side. And there's really nothing physically moving through it because it's electrical, it's not mechanical. But anyway, you have this processor that just knows how to handle zeros and ones. And those zeros and ones have to be in a very specific order. So typically, when you make these most basic types of programs, the way that you would do that is by writing some sort of higher level language and then assembling or compiling that language into zeros and ones machine code. The next closest language for all intents and purposes, depending on the exact system, there could be something between these two. Generally, the next is going to be assembly code. And assembly code is instruction set specific, meaning it's only designed to work on one CPU architecture, one specific rule book that the CPU will follow in terms of how it's going to read zeros and ones as instructions to do stuff. And that's called an ISA, an instruction set architecture. And again, I've mentioned this previously, but there are different instruction set architectures for different types of CPUs. Like you might have a RISC architecture, a reduced instruction set, like RISC-V, or you would see it as RISC-V, the Roman numeral. Or you might have the ARM, like you would have in the new Apple Silicon Macs, or the Raspberry Pi, or a Snapdragon processor in a smartphone, an Android smartphone, something like that. And even the new Snapdragon X Elite chips that are in some Windows laptops with new AI features. And these processors are going to have instruction set architectures that they follow. And then when you go to write some higher level code, like machine code or assembly code, then that assembly code is also specific to that architecture. So you might write x86 architecture assembly code, which then gets assembled by an assembler into x86 machine code, and then run through an x86 processor. So that's pretty challenging to keep all those things in sync if every time you want to write code, you have to think about every architecture that your code might run on. Because maybe you want to write something that you want to work on a Raspberry Pi and an iPhone and a a Windows desktop with an x86 chip, maybe a RISC-V chip that might come out 2 years from now. So how do we solve that problem? Well, most people aren't going to be writing assembly code, and they're certainly not going to be writing machine code zeros and ones. In the say 70s and 80s, 1970s and 80s, it was more common for the average programmer to know a good bit of assembly language, because it is technically a human readable higher level language. It's not zeros and ones. It consists of sort of English-like instructions and sort of numbers, and you might have symbols, and you have basic arithmetic operations like add and subtract, and memory operations like move to put things from memory to registers so that you can do math on them and such. And humans can learn those assembly languages, and they can write them, and then they can just use an assembler to take their assembly language and turn it into zeros and ones that the CPU can read and understand. So that was typical in the 70s and 80s because there wasn't as much you could do with high-level languages. There wasn't quite as much variety in terms of what you could do, and there also was most compiled code was compiled from the C language. It's a very foundational language that's still very much in use today. There's a lot of applications, very performant. It's also difficult to write code in C that is safe, meaning that it doesn't do things that kind of cause crashes unexpectedly. Other languages are better at preventing developers from doing dumb things that cause problems. And but because C was assembled into assembly language and then compiled into assembly language and then assembled into machine code, it was pretty common, and it is still common to some extent today, for developers to know a little bit of assembly code or a lot of assembly code, as they kind of understand the relationship between the C code they write and how that C code is turned into assembly language. Because, for example, you might be able to observe a pattern in the assembly code or something that you do in your C code is compiled into, let's say, a very inefficient set of instructions on your architecture. So you might modify your C code, and then your assembly code changes into something that's more efficient, and that would be a way to optimize at that very low level. Or if you're really knowledgeable in assembly code, and as I said, this used to be much more common, people would actually write entire programs in assembly language, and some very intelligent people do that today as well. I personally can probably count on one or two hands the number of full programs I've written in any kind of assembly code, and I can tell you they weren't very long. And there's a good reason for that, because it gives you a really good understanding of what the computer is doing with your code, with your commands. But it's also just a nightmare to keep all of that stuff in your head. Remember what everything does. Remember how to deal with simple programming concepts, like even just storing variables and doing loops and conditionals can be quite challenging to wrap your head around in assembly language. So a better alternative is to use a compiled language. So I've used the word assembled. I'm using assemble to refer to the step of taking assembly code, assemble like put something together, to assemble a binary. Binary means true or false, 0 or 1. And when we say binary in computing, that often means a program that is zeros and ones that is standalone and can be an executable program all on its own, usually without external dependencies, but sometimes it needs to bring in some external dependencies. And so that would be the step going from assembly to machine. And then we have compilation or compiling, which refers to more generally the process of going from a compiled language like C all the way down to machine code, or it could be maybe just part of that process, like for example the step to go to the assembly code. Or maybe some advanced compilation systems could do a different set of steps, but ultimately they are going to need to adhere to that instruction set architecture. So the thing about compilation and therefore also assembly is that the compiler, the thing that does the transformation of compiled language code, high-level language code like C code, Rust code, Go code, is that the compiler needs to be able to choose a target or a set of targets, which means the type of ISA, instruction set architecture, that the finished zeros and ones binary executable thing is going to be able to run on. And it could do that for multiple. So you could have compilers are these very advanced pieces of software themselves that people put a lot of research and development into making and optimizing and having them create really good binaries. And they can create binaries for all sorts of architectures you probably never even heard of. And so you could have your compiler take your one C code and compile it for, say, 10 different ISAs, 10 different types of CPU, and all those zeros and ones are going to look a little different because the ISA is different. But the program is meant to do the same basic thing. So it's a really convenient way to have programmers just learn a high-level language like C, and they can apply that skill set to managing memory and data and doing arithmetic, which is what most programs are built on, as I mentioned. If they can do those basic operations with a high-level language, they can open up a lot of possibilities as to the things they can do. You know, they can interact with operating systems using C. They can create loops and conditionals and functions and all sorts of things you're familiar with if you've ever programmed in any high-level language. So why do I keep talking about C? It's, like I said, it's a very foundational language. It's also the language that a lot of operating systems themselves are built in, or at least that they used to be built in primarily. It's so foundational. You can write a piece of C code that is your operating system that is the only thing the computer runs. You can set your computer up. It would take a bit of effort, but you could set your computer up to just run your own custom operating system that was a C program that you wrote, made for your computer architecture, compiled to a binary, and then you just have to make sure that the computer knows when it turns on, hey, go run this. And that's essentially what's happening when you boot into your operating system. Your computer hardware talks to your computer firmware, and your computer firmware decides where it should go to look for your operating system, and then your operating system is pretty much just a program, some software, a binary that it runs, and then it is able to provide you all of the luxuries that you're used to from your operating system. And if you noticed, I said operating systems used to be made primarily in C. They're still largely made in C or C++, which is C with more features, different features. It lets you do everything you can do in C, but also more different things. And now there are also other compiled languages that are starting to compete with C in terms of its performance. So C is pretty bare bones. As I mentioned, pretty hard to write really high quality C, but with the building blocks it gives you, you can do pretty much anything. And so a lot of even higher level languages, the interpreters and the compilers, are going to be built ultimately in something probably made with C. And then, people use programs made in C to write more C. So C is very, very important. But now that we have other languages that start to compete with the efficiency of C, we can use those languages to do the same sort of thing. So Rust is a good example of a very highly performant language you may hear referred to as a systems programming language. What that means is it's able to create machine executables, binaries that are ready to run on your computer. They don't need extra software, extra add-ons to be able to do their thing. They can go right down to zeros and ones and be able to run on a computer system without a system being there to support them. And they also have a lot of features that make it easy to do things that operating systems need to do, like for example, setting alarms is something that you can do with an operating system. You can say, I want to ask the operating system to set me an alarm, like an alarm clock, and then it'll let you know when that alarm has gone up. For example, timekeeping is something operating systems will do for you. And so they have, different faculties that allow you to either build a computer system, an operating system, or to make software that interacts very closely with an operating system. Now, the reason C has been so dominant for so long is that it is so performant. When you create C programs, they're often very small. They're pretty much as small as they could possibly be. Maybe you could make them a little smaller by writing the assembly code or the machine code yourself, but obviously that gets very challenging when you have programs that grow to be thousands or millions of bytes long, meaning, a byte is about the size of a letter, an English letter. So imagine millions of letters worth of code. To have that millions, billions, thousands even of bytes of code is going to be very hard for you to manage. But C can help you to do that. You might have thousands of lines of code, but it's pretty human readable, and it gets compiled into millions of bytes of zeros and ones. But those are really small because they don't really have, there's not really a lot of extra frills or a lot of fluff that goes in there typically. And you have a lot of control over what goes in there. You can strip out unnecessary components and just kind of have the minimum you need. So a hello world program in C that you run on the terminal is going to be very, very small compared to the same program that is in, let's say, C# when the piece of C# that is needed to run it is included along with it. I'll get to that in a minute. But like newer languages are starting to rival C in terms of their ability to create really small binaries that are also efficient. C binaries are very efficient. They do things very quickly. These compilers have been so well developed over the years that they optimize your code down to the last little shred of performance to make it as fast as possible to run and as small as possible to create. So, programming languages also have different paradigms, different ways they ask developers to think, because they're not necessary. Programming languages aren't needed. Technically, we could just write everything in machine code by hand and it would take eternity. Or we could do it in assembly language and it would take half of eternity. Or we could write it in C and it would take, 45 years. Pretty good compromise. And then, we can get to other languages that maybe are easier for us as individuals to think in and write good, safe, high quality, fast code. And maybe we could write the same thing that would take us, a couple months in C. Maybe we can do it in Python in, 4 days. So why is it so much easier, and why can't we have it all? Why can't we have the efficiency of C and the convenience of Python, say? Well, a lot of people are working on that problem and trying to make different programming languages that will do something just like that. But by and large, there's going to be a trade-off between the developer experience, how easy it is to write in the language, and then the performance of the ultimate thing. And that's because computers do have to make everything up in this, doing math, moving data around headspace. And to do all of that yourself makes it harder to think about more advanced, higher levels of abstraction in your code. So an example is in C, whenever you want some memory, some RAM memory, random access memory, and you want to say allocate some locations in memory so that you can place an array of numbers in there, a list of numbers. You have to specifically ask the operating system, hey, I would like some memory. I would like this much memory, and it will give you the starting address of that memory. It'll say, here's where this memory starts. I gave you what you wanted. Now the operating system may actually give you virtualized RAM, meaning that address isn't real. It's a fake address that the operating system manages, and it helps with security and a bunch of different things. But for you, as far as you know, you have however much RAM you ask for. So maybe you want to put like 8-bit 1 byte letters, chars they're called in C, an 8-bit number or a letter, and you want to put 100 chars in memory in an array. So you're going to ask for 100 bytes, and the operating system is going to give you back what you think is a contiguous, meaning connected, a space of 100 bytes, and it's going to give you the starting address. Like, think of a row of houses on a street, and you're allowed to use all 100 houses, and they give you the address of the first one, and it's 15. And if you go down to 115 or 114, if I'm off by 1, then you have all those houses there. But C is also not going to stop you from doing certain things like overrunning your memory. So it's only going to give you that starting address. You have to do all the math. If you want to put something in at address 45 between 15 and 115, you're going to have to do that math and decide how many houses you have to move, put your data in there. You're like, okay, this doesn't really make sense. I'm kind of confused, but okay, I trust you. Well, if you were to do that same thing in Python, you would just say, I want to have a list, and you don't even have to tell Python how many spaces you want. It's just like, we'll figure it out later. So you make a list, and it has nothing in it, and then you start adding those chars or those houses or whatever your items are, and Python's just like, yeah, I'll just make your space bigger when I need to. So you can have this now, and then later I'll give you more space if you need it, and it's no big deal. So that's an example where Python manages memory for you. C would not do that. Python will do that. Makes it easier for you, but there's some overhead associated with that. meaning that the Python is going to incur some cost on your program for doing that. And the cost might be speed, it might be the size of the collection of binaries that you need to run your Python code. Like, for example, Python, you have to have the Python interpreter available so that when you say Python space, myfile.py, you need to have that Python executable, which is a binary, and then that runs your Python script. So your Python script isn't actually zeros and ones. It's just a script. Python is zeros and ones, and it interprets your script. And so your script may be small, may only be however many letters are in your file, literally curly, or not curly braces, but colons and new lines and letters. And that may be how long your Python file is. But you also have to count for the entire size of the Python interpreter. And so when you consider that, what's required to run your program on a computer becomes much larger, and there may be a speed cost to that. There also may be a memory cost, because in order to provide you that list in Python that can grow or shrink in size dynamically without you having to do anything, Python has to keep track of all that stuff. And it may lose track of things, and it may use a lot more memory ultimately in the management of your memory for your actual program. It may actually use more memory managing it than you're even trying to use, and at the ultimate code business logic level. So you see there are just some trade-offs there, and like I said, people are trying to make best of both worlds type languages, but as such, as of yet, you still tend to see trade-offs. Rust has some cool things it's doing in terms of the way you think about your code, and it ultimately produces pretty safe code that is very efficient and small, but it doesn't mean that it's perfect. And I can tell you, if you try to jump in and write Rust, it's going to be a lot harder than writing something similar in Python. More efficient and smaller in terms of total machine code and source code. Maybe not source code, but machine code. And in the case of Python, the interpreter plus the source code may be smaller when you compare those two things, and faster, but it might be a lot harder to write. And that does matter, especially when your performance differences or your size differences in what comes out on the other end is not that big of a deal. Like, you have a terabyte hard drive and your executable is a couple kilobytes, so a couple thousand bytes on the C or Rust side, and then your Python interpreter plus your Python script is, I'm just going to throw out a number, 500 megabytes, which is way larger, huge orders of magnitude larger, but in the scheme of your terabyte hard drive, who cares? And when you run the performance, maybe the C program is twice as fast than the Python one, but guess what? Maybe that 2x is the difference between a half a millisecond response time for your user and a millisecond. And humans cannot detect differences that small. So that may not matter in the context of what you're doing. And so you would be probably smart to spend a day writing your Python program and deploy that to your users, rather than spend 3 months learning how to write perfect C for your program and then having essentially the same experience on the other end. But anyway, these are kind of two extremes that I mentioned. Python, where it runs an executable that in turn interprets and runs your code as it reads it line by line, whereas the C code is going to go through a compiler, not when the user is running it, but at kind of development time. You'll write your C code, it will be compiled before it's ever been given to the user into zeros and ones, and then your user will use the binary itself, not the source code. So what's in between here? There are also languages that take a different approach, where sometimes they'll allow you to have multiple experiences. Like maybe you can compile your code, but you can also interpret your code. An example of that would be Go. So you can run the Go program and pass it a Go script, some file.go, and it will run a thing kind of like the Python interpreter, but it's the Go interpreter, and it's going to run your code kind of live. You may also have a Go program that is compiled, so the Go compiler will take your Go and then turn it into a binary as if you had written it in C and compiled it. And then that binary can run right on your hardware. But there's an exception, because Go is a pretty pleasant language to program in. It's kind of, reminiscent of, say, Python. Not quite as challenging to manage things as C. Like, for example, with memory management, it's not going to be quite so hard for you to do that. So there must be a catch, right? And there is. Go uses a runtime that runs your code. So even when you compile to a binary, you get that runtime packaged into your binary as part of it. So it's kind of like we took the Python interpreter and our Python script and mashed them together into one executable that does our Python script and our Python script only. And I think there's probably some sort of fringe tools or even mainstream tools that'll do that for your Python. But the advantage of Go is it's pretty slim in terms of its footprint of this runtime on your program. So I don't recall exactly how big Python 3 is, but let's just say it is that 500 megabytes. I think the Go runtime is something like 12 megabytes. So when you make a Hello World program in Go and you compile it down to an executable, the comparable C program might be 1 kilobyte or 10 kilobytes, 1,000 bytes, whereas the Go program might be 12 million bytes. Big difference, but still very small in the scheme of your gigabytes or terabytes on your hard drive, which are billions and whatever 1,000 times a billion is called for terabytes. So very, very small still in the scheme of things. And you get a lot of nice convenience features in Go as a language for having that runtime piece. So now we're kind of still close to the low level side, the C side. We've talked about C. Rust also is one of these. It's kind of somewhere between Go and C, I would say, where you can have Rust interpreted by using like cargo run. Cargo is kind of the package manager and runner tool for Rust. You use like cargo run to run a Rust program in real time, or you could use cargo build to turn a Rust program into an executable, and that executable is going to be very efficient and slim, just like a C executable, very small, on the order of a kilobyte, 10 kilobytes, 100 kilobytes, or something like that. 1 megabyte maybe for a larger program, let's say larger simple program. Whereas if you go to Go, Rust doesn't have a runtime that comes along with it. It goes straight into instruction set specific machine code. Now the Go is going to go into an instruction set specific binary, but that's going to have that roughly 12 megabyte a runtime that gets put along with your program. So your application logic may only be a couple hundred or thousand or million bytes, but you're going to have this 12 million bytes of the runtime in there. Now, if you go up another step, there are languages like Java and C#. So what is their approach? Java and C#, I think Java, I could be wrong, but I think Java was earlier, and C# is kind of considered colloquially as Microsoft's copy of Java. I'm not sure if that's actually factually true. So you'd have to double check, but essentially the idea with Java was, I think they had this slogan of, and you'll hear this slogan in a lot of contexts, but write once, run anywhere. And the idea was we have all these instruction sets, and we have to write C, and we have to compile it for all these different architectures, and we might have little weird bugs that happen because one architecture supports some feature and another doesn't. So the compiler will create binaries, but then they behave a little differently on different computers, unpredictably. So Java had this philosophy that let's make this Java virtual machine, the JVM. And I should also point out Go is not a predecessor of Java. Go was probably largely inspired by Java and is much more recent development, but it is closer to the hardware in the sense that the runtime is very small. And actually, I don't know the size of the Java virtual machine at the runtime, so it could be smaller than 12 megabytes. But depending on if you can sort of strip out smaller pieces of it, I'm not sure. But I think generally the Java runtime is on the larger side because it supports a lot of features. And what you would do is write your code in Java, and then the Java runtime, the JRE, would run your program on the user's computer by interpreting either Java code or more typically interpreting an intermediate language. We have another intermediate language called bytecode. So when a Java developer writes Java, they can test it in development, kind of like, Go, running Go code, or running Rust code with cargo run, where they haven't compiled it yet. And then when they actually want to have the most efficient, small, executable, distributable thing for their users, they'll go and compile it. So Java will do a similar thing. It'll do a Java C, or it looks like one word, so it looks like Javac. They will Javac their code into bytecode, which is a representation that the machine will not understand. It's not instruction set specific, it's Java specific. And then programs that rely on Java or are made with Java then require the Java virtual machine installed on the computer where you want to run that Java code. So if you've ever installed a program that used Java and it said, oh no, this program requires the Java runtime, 6 or 8 or 12, I don't know what they're at now, then it might install that as part of the installation process, or you might have to go and install that separately. And so that's going to make sure that they can give you a very small piece of an application distributable product, this bytecode, and then that bytecode can talk to the Java runtime, and then the Java runtime in turn is that piece that can be compiled. It is itself a program that can be compiled for different instruction set architectures. So you might have 10 different versions of the Java runtime, the JVM, the Java virtual machine, for different instruction set architectures, but all bytecode can interact with the JVM the same way, regardless of which JVM that it's interacting with. So that's why you can write your code once, compile it once to bytecode once, and then distribute that bytecode to any compatible JVM, meaning any JVM of the correct version of Java. Not the ISA doesn't matter, but the version of Java might matter. Certain features that come out as Java progresses. And that gets into this idea of the difference between kind of code that is application specific and then code that is shared between applications. So the nice thing about having shared code is that you can have one thing that has a certain footprint on your hard drive and that you're going to have to install, but then you can run lots of programs with that. So Python works this way. You install Python 3 on your computer, and then you can write these tiny, tiny little Python scripts that might only be hundreds of bytes long. And regardless of how long the executable for Python is, you might have 100 or 1,000 different Python programs on your computer that can use that same interpreter. And so that's efficient, because if you were to say, okay, we're going to make 100 separate programs that are C programs, and they go right to machine code, and each one of those comes out to being 100 kilobytes, or I don't know, I'm probably going to get my math wrong now, but you have 100 kilobytes times 100 apps, and so you have 10,000 kilobytes of footprint on your hard drive. And then you might have the Python interpreter, and let's say you have 100 programs, but they're only, let's say, 10 kilobytes each. So they're a tenth of the size, because it's just the script itself, and it doesn't contain any instruction set, architecture specific stuff. So now you have, instead of having 10,000 kilobytes of programs, you have 1,000 kilobytes or a megabyte of, so 1 megabyte versus 10 megabytes with C. But now you need the Python interpreter. But the convenience is you don't have to have 100 different Python interpreters, you just have one. So you have your 1 megabyte of scripts, and then you add that to your 500 megabytes of Python interpreter or whatnot. But you can see how that scaling is to your advantage as you get more Python programs. If that were the case, I'm not saying specifically every Python program will be smaller than the comparable C binary. That's not necessarily true. But let's just say, for sake of argument, it were true, and you have, as that number of programs you have scales up, your cost of the Python interpreter per program goes down, if that makes sense. And that can apply to really any type of shared code. So even when you have C code, I'm going to introduce something that's going to probably challenge you a little bit now. When you have C code, you can compile your C code into executables, zeros and ones, like I mentioned, binaries. But another way you can compile your C code, or you could also do this with your Rust code or different compiled languages, is you can compile them into a shared object or a dynamic library, or a shared dynamic library, some combination of those words. On Linux, this would be a .so file, shared object. On Windows, this would be a .dll file. You might have seen that with like a plugin for a video game or something. But a shared object, what that is basically a dependency for a program that can be shared by multiple programs. So you can install one shared object on your computer, and then a bunch of different binary programs can call that external dependency and all rely on that thing. So whereas if you had statically compiled that portion of your application, let's say your application does tasks A, B, and C, and you take task C and you compile that into a shared object. Well, now your binary goes down from including A, B, and C to including just A and B. Now your shared object has C. So now if you go to write another program that does tasks C, D, and E, now you only have to include D and E in your regular executable, and your shared object already has C, right? So you can just find that same shared object on the computer, and both of those programs can use that same shared object to avoid that duplication in machine code on your computer, reducing the overall footprint of a larger number of programs. So if you just have one program, this isn't going to be to your advantage, but if you have multiple programs sharing the same dependency, it can be to your advantage. And there's a big parallel here between using, say, a shared object, where the shared object is a binary and then your actual application code is a binary, and something like Python, where Python is a binary and then your application code is a script, but it kind of interacts with that Python binary. And so you can avoid duplication in that way. And this is the same reason when we write code in any language. When we have a task that we do a lot, we will create a function for it, and then we'll call that function. We might call that function in 10 different places, but our application code only needs to contain that code once. If you ever find yourself taking code that you wrote and copy and pasting it into the same project in multiple places, you should think again, because you probably need to make a function so that you can have that code just once. And then if you ever want to make a change to it, you don't have to make a change in 10 places. Just make a change in one place, and it's reflected in all the places that call that particular function. So I hope this is starting to make a little bit of sense. And once again, this applies to shared objects. When we talk about compiled languages, it applies to Python, which is an interpreted language. And it also applies to those languages that fall in between compiled and interpreted, like Java and C# and Go, where their interpreter or their runtime can be one place and then shared by different programs. And I've never done this myself, but I'm guessing there probably is a way to do this. If you wanted to say compile a Go program, and rather than including that 12 megabyte runtime in each executable, you could probably somehow have that be a shared object, or more likely you would just have Go installed on the computer, and then your Go programs could all use that one source of Go's features and be quite small individually. So Java and C# are big on this concept where they say, we're going to give you a lot of advantages to having this virtual machine, this JVM, or in C#'s case, it's called the .NET runtime, if you ever heard of that. So you can make code that targets, meaning that its intended running location, the place it's made for to run, is the .NET framework. Once again, that's something where you might have installed a Windows program where the .NET framework was required, or a certain version of the .NET framework was required as part of the installation process, because the application developers wanted to draw on a lot of those features from .NET without having to include it in their application binaries. And that way you could have, again, you might have 10, 20, 100, 1,000 Windows programs on your computer that all use the .NET framework, and then that .NET framework, whatever footprint it has on your computer, is spread out between all those different programs rather than being included in every one. So one of the advantages that you get when you go a little bit further, I'm not sure that Go does this with its very small runtime, but I know C# and Java do this with their runtimes. Again, I'm not sure of the size of them, but one of the features that they provide is by going to these intermediate languages that the runtime or the virtual machine can run, you get advantages as your code is running when it actually goes to run. So what do I mean by that? Well, your code is written in Java, or it's written in C#, and then you compile. They use the word compile loosely here. You compile, or you build your code not into zeros and ones, but into byte code in the case of Java, and something called IL, which I think is intermediate language or something like that, for C#. And this IL and this byte code then talks to their respective runtime or interpreter that has to be installed on your computer typically, and you get advantages like JIT, just-in-time compilation. You may have heard that. You may be wondering what that is. What that means is that the interpreter, the runtime, is going to, on the fly, so as your program is running in real time, whenever the user actually goes to execute your Java or your C# app, in real time, the runtime is going to talk to your application code, and it's going to turn your application code in real time. I mean, it must eventually come down to zeros and ones, right? So that's why it is zeros and ones. The runtime itself is zeros and ones. But what these two specifically will do, and I'm sure there are others like them, is that they will give you compilation of your code, not just the code of the runtime, but compilation of your C# and Java bytecode or IL, and it will put that into instruction set specific machine code on the fly, Now, why would you want to do that? It's like, that's dumb. If you were able to make machine code, why didn't you just make me machine code from the beginning? Well, what they're doing is they're running your code and they're dynamically observing how your program acts. So your program does certain things by interacting with the runtime that creates patterns of zeros and ones that get run through the CPU. That's what happens. But the runtime is smart and it observes what you do. Based on what you do, it creates machine code optimizations in real time, like a compiler does this at development time. Java and C# runtimes will do this at runtime, which has an advantage because it allows you to see patterns in how you're running your programs that weren't necessarily clear at build time. If you're thinking, how could that be? Let's say you have functions A, B, and C in your code. And now at build time, so at runtime, your users can call A, B, and C however they like. And you don't know how. Maybe it's a HTTP application, and when somebody puts into their URL bar localhost/A, it does function A, localhost B, it does function B, and so on. And so your app just knows, what do I do when somebody talks to me on localhost A? But it doesn't know how many times someone's going to use A versus B versus C. So at build time, there's no way to optimize that to say, well, we know that A is going to get called a lot, so let's really prioritize the program to be around A. But what Java or C# can do with just-in-time compilation is that they can see, okay, your users are calling A 90% of the time, and they only call B and C 5% of the time. So it can then restructure the way that your machine code is being given to the CPU so that you actually get better performance as your program is running, and it can kind of dynamically adapt over time based on conditions that happen as the user is running your program. And this is a big distinction that you're going to want to learn in general, is the difference between build time or sort of like static code analysis optimizations, and then runtime optimizations, where things are actually actively happening with your code. Your code is being used, and then something is adapting to how things are going at runtime. And that's how Python can do things with the interpreter at runtime. The JVM can do things at runtime, whereas the C compiler, everything is done once it's turned into a binary. The C compiler no longer has any influence over your program once it's turned into a binary. That binary is now complete, it's done. There's no more optimization happening. Any optimization that happens would have to be done inside of your application code that was compiled. So, at that point, we've talked about the compiled languages. We've talked about compiled languages that can include a runtime in their binary, like Go, that has a relatively small footprint but gives you a lot of these developer conveniences. You have Java and C# that do just-in-time compilation to give you advantages. Talked about those different ways that you can share code between applications, whether that's a shared object, whether that's just a function in your code, whether that's one of these virtual machines that you have on your computer once and then all the programs can access it, or you can go to the very kind of extreme of developer ease and have a very large interpreter like Node.js or Python installed on your computer and just run scripts. And one little comment I'll make here is on the difference between scripts and code. I like to think about this as a script is like a play script. The actors or actresses read the script from top to bottom, and they just kind of, they just say what's in the script one thing at a time. Now, you might think, well, code does the same thing, right? You write code, and it gets run from top to bottom. Yes and no, it does. But the thing about code more generally is that you might have it compiled into machine code. So whereas your C code, it looks like one thing, that doesn't mean that you're going to have necessarily, there may be a C interpreter out there. I'm sure there is. If you want to run C in the browser, I'm sure somebody's made an interpreter for C. But generally, C code is not necessarily being run from top to bottom. It's being optimized by the compiler into an executable that is run from top to bottom, or from front of the zeros and ones to the back of the zeros and ones. And then, when you have an if statement in it, or a function, it gets to a thing that jumps to another place in the binary so that you don't exit out of the binary, and you can keep it running until the user tells you to stop or something like that. And scripts can do the same thing, but the difference is, really, I might be confusing kind of what's the difference between code generally and scripts. I would just say that scripts think about scripts as being read. They usually, when you have a script, you have an interpreter, something that is reading your code line by line at runtime. Whereas when you have code more generally, code could be a script, or code could be something like C code or Rust code that isn't going to be read by an interpreter at runtime. It's just going to, it's just the building blocks from which a compiler will create a binary, zeros and ones, that will then be read from top to bottom. So in that case, it's kind of like the binary is your script that your actors are going to read, whereas for a scripting language like Python, your Python interpreter is going to be the reading the script itself, the actual source code. I think finally, something I should mention is that I've already kind of touched on how languages like Go could be interpreted or compiled, and they might be even very fast or very small footprint on your computer when they're running in the interpreted mode, and so there may not be a need to compile them. But I think the examples of Java and C# are really good for illustrating the point that the full kind of spectrum. So C# is an example where modern versions of C# are moving towards where certain programs that don't use a ton of external libraries, there's kind of caveats with this, but C# can now do something where you can run it in a lot of different modes. So you can run it in kind of the development mode. You can run it where it is small. Your executable is small because it's IL, but it's going to need the .NET framework installed on the computer to run. You can also have, kind of like Go, you can have the .NET runtime put inside of your binary so that it is standalone, but then obviously, like Go, it becomes larger. That binary becomes much larger because it includes the .NET framework, but the C# compiler can do smart things like take out all the parts of the .NET framework that you don't need and only include the ones that you do need. But you still might end up with something that's 35 megabytes large compared to, say, 12 for Go, or just mere kilobytes, thousands of bytes rather than millions, for just a C# IL code that depends on the .NET framework being installed on the computer. But now, with very certain situations, and there are, like I said, there are a lot of caveats to this, C# actually has the ability for you to target native machine code with your C#, and it will strip out most of the components of the .NET framework. And so you can end up with a very small, very efficient binary that you wrote in C#, which is a higher level language that's probably easier to work in than C, for example. And you could end up with a very slim in size and fast binary, just like you could create in Rust or C. So that's a great example of C# being this full spectrum, where it can run with a runtime, it can include that runtime in the binary, or it can even create binaries that are standalone and don't include most aspects of the runtime. So I think that should wrap it up for today. That gives probably more than you've ever wanted to know about these different types of programming languages and how they work, and what are the kind of trade-offs between choosing different methodology or approach for a programming language that you might choose to use. So thank you for listening. I will catch you in the next one.